Good morning, everyone. I'm Qian from Alibaba Cloud. Today, I will present ServeGen, our work on characterizing and generating realistic large language model serving workloads in production. This work is conducted in collaboration with Peking University. In the past few years, LLM serving has become one of the most critical cloud computing tasks, as it continues to power new applications. At Alibaba, our production system serves billions of requests daily across language, multimodal, and reasoning models. The scale and the diversity of demand drives the search for better serving system design. And the workloads are a big part of this process. Every design decision, scheduling, auto-scaling, resource provisioning depends on workload assumptions. They motivate new optimizations and measure end-to-end performance. If workload assumptions are wrong, system designs will be wrong too. This begs the question, how well do we actually understand LLM serving workloads? The answer, unfortunately, was not so much. Back when we started our work, characterizations on LLM serving workloads were limited, with only 2 prior studies. Among them, BurstGPT conveyed only 2 language models with 5 million requests, and LLM analyzed only image workloads over 2 days. A lot is still missed, both in scope and scale. First, the rapid emerging omni-model and reasoning workload remain completely uncharacterized. Second, even for large language model, which have been studied, the limited scale had left many intricate patterns unexplored. The lack of workload understanding also means that researchers had to rely on unrealistic ways to generate workloads and benchmarking. In fact, combining person arrivals with shared GPT becomes somewhat of a standard. But as we will see, this approach actually produced misleadingly easy workloads, creating a gap between research and production, and we want to close this gap. That's why we set out to build ServeGen, where we characterize real serving workloads at Alibaba and share our findings through a realistic workload generation framework. We end up with 3 contributions. First, ServeGen is the most comprehensive LLM serving workloads characterization to date, with 3.5 billion requests across 12 models over 4 months, covering language, multimodal, and reasoning workloads. Second, we found an empirical causal model. Decomposing by client reveals that a few top clients steer the complex patterns we observe. Third, using this insight, we built an open-source framework that generates realistic workloads using the per-client approach. In the rest of this talk, we will first walk through some of the interesting findings in our characterization. Then I will show how ServeGen turns these findings to a practical workload generator with 2 case studies focusing on the system's implications. Let's start with the large language model workloads first. First, arrival pattern. It is unsurprisingly to find that the request arrivals are bursty with CVs well above 1. But for LLM serving workloads, it is not just bursty. The pattern is complex. Across multiple models, we found that no single stochastic process fits all workloads, as shown by the fitting curve for different workloads. The best fit can be exponential, gamma, or other distribution in each case. The case tests on the right confirm this difference are statistically significant. Further, the burstiness itself shifts over time. Look at M large, the red line in the figure, which represents our flagship model. In a week's time, its arrival pattern was continuously bursty for 2 days before turning to stable. And these burstiness shifts don't happen in sync with the reshift, making them harder to predict. In summary, One should not assume a single fixed pattern when it comes to modeling LLM serving workloads. Static workload assumptions will fail, and the system needs an adaptive design. Beyond arrivals, request length also matters. They determine compute load. For input length, we find a heavy tail distribution between modeled as a Pareto and log normal mixture. As shown by the blue curve, the tail is important. Long prompts are real but expensive to serve. We need to feed the body and the tail separately to capture the full distribution. Output lengths, on the other hand, are surprisingly exponential or memoryless, as shown by the orange line fitting curve in the log scale figure. This asymmetry between input and output have implications for how we model, prefill, and decode load. Another important finding is that input and output lengths are weakly correlated at best. You cannot predict how long the output will just from the input length. This means the method that's relying on predicting request length might not easily apply to the general workloads. Finally, a very integration pattern is the length distribution shift over time. For example, the M-middle workload input lengths can shift up to 1.6 between time periods, and output shifts up to 1.46 times. And these shifts are independent. Input increases from midnight to afternoon, while output actually decreases. All these findings directly impact prefill and decode load as the length distribution exhibits different characteristics and independent shifts. Systems need to conduct more fine-grained modeling and resource management. Now, knowing arrivals and lengths are complex and dynamics is informative. But if we cannot model them effectively and act on them, then the findings are not really helpful. Luckily, we have a key insight. When we decompose workloads by client, a clear picture emerged. In this workload shown in the figure, we show the behavior of the top clients, which there are only a few of them. In fact, just 1% clients produces 90% of requests. Each top client is individually stable. This enables a causal model of workload behavior, where clients' rates fluctuations shape the entire workload. Here is one example in action. On the left, we see the client A, the blue line, has average CV of 2.1, while all other clients sits around 1. On the right side is the aggregated rate CV figure which we saw earlier. Note how the blue curve on the right almost mirrors client A's rate curve on the left in the first 48 hours, because client A's bursty traffic was the primary traffic. We can actually model the chaotic burstiness by the mixing of clients. The same goes for the length shift. Client A has a very distinctive input length distribution, average around 65 tokens, much shorter than average. Where client A's rate rises, it contributes more requests, pulling the aggregated input distribution towards shorter lengths, as we can see from the midnight to morning in the figure. This is what we call the causal model. The complex pattern we observe in the aggregate, the burstiness, the length shift are not random or unpredictable. They are caused by the mixing of few dominant clients, each with different but stable characteristics. This is powerful because it means we can model workloads per client and compose them. Later, we will see that ServeGen uses this extensively. That was a large language model workloads. Aside from that, ServeGen also characterized the emerging multimodal and reasoning-heavy workloads. each with their unique characteristics. Here I will highlight one interesting findings from each. For multimodal, specifically omni-modal workloads where requests can contain text, image, audio, and video together. One key finding is that multimodal load is long-tailed. We see up to 63 audio inputs in a single message, and the load for each modality shifts independently over time. You can see the right how image, audio, and video rates measured in number of tokens during the text diverge from the text. This means the LLM backbone is no longer the only focus. Each modality in code needs independent scaling, and the serving system needs full stack optimization beyond just the LLM part. For reasoning workloads, the most distinctive feature is their multi-turn conversation structure. As shown here, the average conversation has 3-point-time terms, with inter-turn times peaking around 100 seconds. That's the user thinking before the next prompt. This multi-turn structure has an interesting system benefits, as shown in this right figure. If we sample requests by keeping the full multi-turn conversation, it smooths out the arrival pattern, making the arrival much less bursty, which opens the door to proactively scheduling, where the system can anticipate the next turn and pre-allocate resources. That's just some of the highlights, and our paper actually covers more detailed findings. Importantly, we show that the causal model with client decomposition generalized to every workload we analyzed. Now let me show how ServeGen turns these insights into realistic workload generation framework. ServeGen is centered around the client decomposition clients. Instead of generating workloads as a whole, it composes them per client. A client generator sample heterogeneous clients from a pool parameterized with real behaviors. Then per client timestamp and data sampler produce arrives and request content, which are aggregated into a final workload. We validate the accuracy of our approach against the actual workload and the naive approach. Here, naive refers to the poison and the dataset sampled method used by many researchers. As shown in the scattered plot, in every case, ServeGen matches the actual workload patterns much better. The naive approach completely missed the correlation between rates and the data distribution. Further, we also apply ServeGen in 2 concrete use cases to show why realistic workload matters. First, instance provisioning. We take 30K requests from one of our real workloads and use both naive and ServeGen to produce benchmark workloads to find the minimum number of VLM instances need to meet SLOs. The heat map shows the results. Naive greatly under-provisions, with most gray cells that indicate too few instances and SLO violation. On the other hand, ServeGen is provisioning in most accuracy with Qian cells across the board. Importantly, we see that naive workloads are misleading easier to serve, which result in wrong capacity planning. For the second case, we look at PD disaggregation. We deploy the 72 billion models with TP4 on 32 GPUs. We vary the prefill decode split and benchmark with both naive and ServeGen workloads. The results show that different workloads disagree on the best configuration. This result shows that PD disaggregation has a high workload sensitivity. It also aligns with our experience of deploying PD disaggregated systems in production. The performance can be less robust on the real workloads. So that we have time for today, but we believe ServeGen can do more. For one, we hope ServeGen fosters further researchers There are many open directions like full-stack multi-panel optimizations, proactively scheduling for reasoning and recent agent workloads, and high-fidelity simulation for serving systems. Meanwhile, our findings have already been useful internally at Alibaba in our inference infrastructure teams. Our framework and data are open sourced on GitHub. We hope it helps the community build and evaluate better serving systems in the future. Thanks for listening, and I'm happy to take questions now.